In this project, the dynamic system being examined is a water tank. It can be anything, say like a bucket, but it has to have a water spout or a hole on the bottom, and it's constantly being filled up from the top. The point of observation, what is being measured, is the water level of the tank. This system was chosen because of its simplicity, and it demonstrates how controls play a part in nearly everything we do, and it also allows for a greater understanding and ease of presentation. So this is our dynamic system. There's the water tank on top with the water spout running down. The inlet flow rate is controlled by this nozzle on the hose, which water comes through, comes out the bottom, and it fills up at the top because the nozzle on the bottom is not open all the way. It can be said that there are two different equilibrium points in our system. One, when there is no flow, when the system is empty. The other equilibrium point being when the incoming flow and the outgoing flow are approximately equal, maintaining a steady level at where we want to be. So this system as it stands right now would be probably defined as an open system, simply because it's currently being controlled by a human. And a human is not going to measure the incoming flow rate and the outgoing flow rate and calculate the error or difference between the two and adjust accordingly. A human's going to simply look at the height of the water and then make necessary adjustments with the incoming water flow based off intuition. In order to make this a closed system, imagine that there is a flow meter at this joint to track the incoming flow of water, and that there is another flow meter within this at this joint to track the outgoing flow. And then there is some system heading back up to the top to send the information from the two to calculate the error in between them and make necessary adjustments to the incoming flow to try to balance out the two. Now say that you're trying to achieve a certain height, say this black line. The two flow meters in conjunction can easily do this by utilizing this equation. You can use the outgoing velocity to track at what level the flow will be. And so that being an input, the system can adjust accordingly. Based off of intuition, it could be said that when there is no incoming flow, this equilibrium point can be noted as stable, because any kind of disturbance will always just flow out the bottom. However, when the water is being maintained at a steady level due to the flow rates being equivalent, if the system is disturbed with more water being added, and then returned to where it was usually at, the system has to work much harder to regain balance. Is there any kind of practical application for an incoming flow and an outgoing flow equalizing to maintain a steady height at some point in a tank? I have absolutely no idea. But that's not the point. What is the point is that because it is such a simplistic system and easy to understand and produce, it can easily be described how it is a PID controller, and that is explained on the next summary slide. In this project, the dynamic system, again, is a water tank with a hole in the bottom. The water tank can be a bucket or whatever. The governing equations of motions in this process boil down to flow rates, and they can be calculated from Bernoulli's equation. So after some mumbo jumbo using that, you get that the height comes out to the outgoing flow rate squared divided by 2 times gravity times the area of the outgoing nozzle. The velocity of the height, because the height is what's being measured, the height's what's changing, comes to the incoming flow rate minus the area of the outgoing nozzle times the square root of 2 times gravity times the height divided by the area of the base of the tank. The acceleration of the height isn't really calculatable just because the acceleration is constantly changing due to the PID control system. Because the spout is never shut and there is always water either flowing or not, not flowing at all, the system is continuous. The input of the system is the flow rate coming out of the faucet going into the tank. The output of the system is the water level in the tank, which affects the outgoing flow rate. The water level in the tank is what's being measured. In this system, positive feedback is being used. When the incoming flow rate is increased, the outgoing flow rate is increased as well. And when the incoming flow rate is reduced, so is the outgoing flow rate, depending on where exactly you're at in the system. So the control law depends on the complexity of the system and whether it is operated mechanically or by a human. As mentioned previously, a human is not going to measure the incoming flow rate and outgoing flow rate and analyze the difference or error between the two. He or she will instead observe the water level and whether it is rising or falling and adjust accordingly. Since our system is not operated by a human and instead is operated by our imaginary flow meters at the inlet and the outlet and the system leading back up that controls the incoming flow and only the incoming flow, the flow meter at the spout and the flow meter at the inlet compare and contrast the different flows coming in and out, and the signal tells the incoming flow just how much that it needs to either reduce or increase the incoming flow. This type of control can actually be identified as a PID controller. Imagine that you are trying to start from an empty system and reach that black line and maintain a level at that black line to have even flow coming in and out when it reaches that point. So you have to originally dump in your incoming flow, choose a set amount that you want to dump in, and since you cannot influence your outcoming flow, it's just a hole in the bottom, you constantly are pouring in water, but your outgoing flow is always constantly changing. It's a dynamic system. So you can only adjust incoming flow, meaning that your system has to adjust accordingly as the water level rises because the outgoing flow depends on how high the water level is. So the initial decision on how much the flow rate should be increased or decreased is described as a proportional gain. Then if the system recognizes that the flow rates are approaching each other, the derivative control takes over and reduces the incoming flow rate. Or an example of the integral control would be if the system notices that the outgoing flow rate is exceeding the incoming flow rate, it would increase the incoming flow based off where you are at the water or where you are in your height.